Hey everybody, welcome back to chemistry. If I can increase the slide. So it reads as follows. Use the van der Waals equation of state to calculate the pressure of 2.6 moles of krypton at 491 degrees Kelvin in a 4-liter vessel. Van der Waals constants can be found in the van der Waals constants table. And as I recall, in that particular problem on Achieve, you can click on that table to get the necessary constants you need. You'll need a constant called A and a constant called B, and you'll have to look up the A, B values for your molecule. So I already did that. I looked up the A, B values of krypton, and so I have them listed there. And then also there, I actually put in the equation you use to solve the problem. And then there's a second part to the problem. It says, use the ideal gas equation to calculate the pressure under the same conditions. Okay, if I can lower the slide. Okay, so what we have here is we have a gas under certain conditions. And so let me go ahead and write those out. And so one thing we know, the gas is krypton, so just keep that in mind. So we know the pressure is something we are trying to find in two different ways. We want to find it using the ideal gas law, which is part 2, but we also want to do it by using the van der Waals equation of state, which is part 1. Okay, so we are told the number of moles of gas, so it's 2.60 moles. We're told the temperature, which is 491 Kelvin. And also we are told the volume of the gas, which is 4.00 liters. Okay, so I think I'm going to just do the easy one first. So let's just go ahead and figure out what the pressure of this gas would be in atmospheres using the ideal gas law. So again, I'm doing part 2 first, so I'm just going to write number 2 here. And so the ideal gas law, I'm hoping you have memorized, it's PV is equal to nRT. So it looks like we have everything. We know the value of R. We can use the one we're used to, which is 0.08206 liters atmospheres over mole degrees K. Okay, so what I'm going to do is solve this equation for P. So what I need to do is move the V. So the V here is in the numerator here. We're going to move it to the other side of the equation. It'll go in the denominator like that. So I can write P is equal to nRT over V. Okay, so at this point, let's just go ahead and plug in numbers. Okay, so N is 2.60 mole. R is 0.08206 liter atmospheres over mole K. And let's see, temperature is given to us in Kelvin, so that helps. It's 491 K. And then we divide that by volume, which is 4.00 liters. And so let me just confirm that units cancel out. So liters cancels out here, moles cancels out here, Kelvin cancels out, and it looks like 80 atmospheres does not cancel out. So that will be our answer. And so when I did this earlier, the value I got, rounded to 3 significant figures, is 26.2 atmospheres. Okay, so I'm going to clean this up, and we're going to now do part 1, which is more difficult. Okay, so now we're going to find the pressure of this gas, but we're not going to use the ideal gas equation. We're going to use a more complicated equation, which is the van der Waals equation, which I have there on the slide. So this is an answer to part 1. Okay, so this is more of a pain. Okay, so let me write out the van der Waals equation as you see it. So we have, in parentheses, P plus a constant A, and then it's N squared over V squared, and then close parentheses, and then you have another parentheses, V minus N times B is equal to nRT. Okay, so what we need to do is solve this equation for P. So let me kind of walk through how to do this. But before I do, I think I want to simplify the n squared over v squared by writing this. So I'm going to rewrite the equation, and then instead of having n squared over v squared, I'm going to write n over v like that, and then squared. And then v minus nb is equal to nrt. Okay, so again, we have to solve for p. So what the first thing I'm going to do is, you see this v minus nb? That is an expression that can be moved to the denominator if you move it to the other side of the equation. So let me write that out. So now we have p plus a n over v squared is equal to n r t over v minus n b. Okay, so now what we can do is, you can see we're not quite done isolating p. Right now, attached to it, we're adding a, and then times n over v squared. So when you need to subtract that from both sides of the equation. So imagine here I'm subtracting out a over n over v squared, and I'm just going to now subtract it out over here. So it will look like this. So what you can see now is that a times n over v squared minus a times n over v squared, that goes away. And so let me rewrite the equation now that we have. So p is equal to nRT v minus mb minus a n over v squared. Okay, so what I'm going to do is I'm going to rewrite that equation up there and then solve the problem. So I'm going to clean this up right now. Okay, so I've rewritten the van der Waals equation of state where I've solved it for p. So now at this point, you can just sort of plug in numbers and just carefully work out the math to get an answer. So here we go. So p is equal to n, which is 2.60 mole. R is going to be 0.08206 liter atmosphere over mole Kelvin. Okay. T is going to be 491 K. And then over, and then V is 4.00 liters minus N, 2.60 mole, and that has to be multiplied by B. And so B is 0.0106 liters per mole. All right. Put that in brackets there. Then we can't forget to subtract that next term, which is A times N over V squared. So A is 5.121 atmosphere liters squared over mole squared, and then we need to multiply this by this number here, which is squared. And so here N is 2.60 mole, and then here V is 4.00 liters. Okay. So let me go ahead and do the math. So first, let me just go ahead and do the numerator first. And so I'm going to cancel out units here. Moles cancel out, kelvins cancel out. So it looks like the numerator numbers in liters per atmosphere. So pressure is equal to 104.757 liters atmospheres over, okay, before I do the subtraction, I need the multiplication first. So it's going to be 4.00 liters minus, I'll go ahead and do this multiplication, and I see that moles cancels out, and so I got 0.02756 liters. Okay, so far so good. Then we're going to work on this term here, and what I got when it was all said and done, I got 2.163 here. And so here it looks like all the units cancel out except for atmospheres. So this is going to be atmospheres. Okay. So here I'm going to get 104.757 liter atmospheres over, I'm going to go ahead and do the subtraction here, and what I got was 3.972444 liters minus 2.163 atmospheres. And you can see that here liters cancels out. So the pressure I got in the end when you do that math is I got 24.208 atmospheres. And I think they want that rounded to 3 sig figs, so it's probably 24.2 atmospheres. And so the point they're trying to make in this problem is that if you use the ideal gas law to calculate pressure, you get that value in atmospheres. But if you use the van der Waals equation, which in theory accounts for non-ideal behavior that gases can have, you get something different, 24.2 atmospheres. You can see it's significantly different. And so this number here is probably going to be closer to the truth as to what the pressure of krypton is going to be under these conditions. So thank you for listening, and we'll see you next time.